Good morning, everyone. Good afternoon, good evening, whichever timeline you are in. A happy day for you all, right? Today we are going to discuss about periodic classification. I am Harita Kasturi from PACE IIT and Medical, Hyderabad. So we are going to do about now the periodic classification today. Why do we have a need to classify the elements? See, we have 118 elements altogether, so many elements altogether. So when these elements are there, 118 elements are present, and we have to consider the classification of these elements to study each of them, because we have so many elements. If we have to talk about the elements, then we have to understand the nature of these elements. And how do we understand the nature of these elements? As we classify them into some groups, right? So the first ever classification is given by Mr. Lavoisier, and even before that, I would like to mark a point that Sage Kannada Maharshi is that person who has given us exact orientation of an atom, how they behave. He is the father of chemistry for all of us. Especially being Indians, we are proud to have such legacy of ancestral history with us. But unfortunately, we are being glorified by the English education, wherein all the European scientists, no less regards to them, but keeping high regards with them as well, we should also consider our legacy of Mr. Sage Kannada Maharshi Sage Kannada, who has given us these theories way before our original classification has been given in the books, in the notebooks, right? So coming just in great regards to him, Sage Kannada, we will start our program, our questionnaire or our discussion on this periodic classification today. And coming up with the first ever classification is Lavoisier. Mr. Lavoisier, Sir Lavoisier, he has given us the classification of the elements as metals and non-metals. But his theory is not been completely agreed, because he did not say anything about the metalloids, which have the properties of intermediate in between metals and non-metals. That properties are being not discussed. Hence, Lavoisier's theory is not widely accepted. Then comes up with your Dobryna's triads. Triads, as the name suggests, triad is three elements together, right? So Dobryna's triads, he has grouped a few elements as sets of three. Now the first set of three is lithium, sodium, potassium, then chlorine, bromine, iodine. So lithium and potassium. Now what is the theory behind grouping them into these groups? He has given all these elements as the sets of three, wherein if I say A, B, C are the elements A and C, the average of A and C will be B, which means A plus C by 2 will be my B there. So it's exactly going by the same way. 39 plus 7 by 2, that is how much? That is your 23, right? 39 plus 7 by 2 is 23, which is exactly the atomic mass of sodium. Similarly, if we have consider ClBrI set, so that is 35.5 plus 0.5 plus 127 by 2, it is somewhere close to 81 point something, so which is also close to 80, which can also be accepted. But where is the limitation? What do we mean by limitations? Limitations are, where are these properties unmatched? Where are these not getting tallied by the properties given by the postulates given by them? So here is the postulates, here is the point wherein it is not being matched. NPAS, nitrogen, phosphorus, and AS, wherein 14 plus 74.9 by 2 is nowhere close to 31, so which means it is not accepting that triad rule, right? So these set of elements are not accepting the triad rule, yet they are being put into the triad configuration, so that properties are not being explained by him. So here comes the limitations of these triads also. Then comes up with with our next kind of classifications. This is Newland law of octaves. This is very interesting. Law of octaves. Octaves, as the name suggests, it is a set of 8 elements. Every 8th element will behave as the similar way. Like if I say it goes by the musical notes, are very interesting musical notes. Sa, re, ga, ma, pa, da, ni, again, sa. I'm not singing, don't worry. Okay, sa, re, ga, ma, pa, da, ni, sa. So, sa, re, ga, ma, pa, da, ni are the 7 things, 7 notes, and then again comes up with 8th one. Similarly, in the English European music as well, we have do, re, mi, fa, sol, la, ti. Do, re, mi, fa, sol, la, ti. Again, do. Again, do. So, all these 7 elements, again, the next one, the 8th element will be repeating. So, exactly going by the rule. If I talk about hydrogen, hydrogen has a repetition of the properties just like your fluorine, right? Because hydrogen accepts 1 electron and become hydride, H minus. Similarly, fluorine accepts 1 electron and becomes fluoride. Similarly, chlorine accepts 1 electron and becomes chloride, Cl minus 1. So all these are behaving the similar way, right? And that's the reason they are being put under the same group, which is same column, right? So going by the same thing, if I talk about beryllium, chalo, beryllium. So take beryllium as number 1, then 2, 3, 4, 5, 6, 7, 8. So 8th element for beryllium is magnesium. And similarly, I take nitrogen. 8th element for nitrogen is phosphorus. After nitrogen, nitrogen stands at 1, 2, 3, 4, 5, 6, 7, 8. So 8th element is phosphorus here. So likewise, you go with any element. 8th element will have the similar properties, and that is what his postulate means, that every 8th element behaves the same way as the first element. Now, what are the limitations then? Why are the limitations given? Because this is the kind of periodic table that he has shown, wherein his rule is applicable only till calcium, only till lighter elements. Next, coming up, heavier elements are not obeying his rule, not obeying this rule. Like, for example, if I say cobalt, nickel, iron, all these have similar properties of, magnetism and all, right? But they are not being put under one group, and moreover, two elements put under one group. Why? Reason not being explained by him. Then also he did not give anything about the noble gases, right? See, do you notice that after hydrogen there has to be helium, after fluorine there has to be neon, after chlorine there has to be your argon. So like that, there is the whole set of noble gases missing there. So he could not explain anything about the noble gases, and he could not give the position of hydrogen clearly also, because hydrogen, yes, it behaves like halides, halogens, which are your fluorine, chlorine, bromine, iodine, but it does behave as the group 1 element, as it does behave as lithium also, right? Hydrogen leaves away 1 electron to become hydrogen plus, hydrogen ion. Similarly, like lithium leaves away 1 electron to become lithium plus, or sodium leaves 1 electron to become sodium plus, potassium plus. So likewise, this hydrogen also behaves as the group of lithium, sodium, potassium also. Then why is it hydrogen is not placed under that set? It is not been explained by him, right? And moreover, isotopes. What are isotopes? Isotopes are nothing but the elements having the same atomic numbers but different mass numbers. If I say hydrogen 1, 1, hydrogen 1, 2, hydrogen 1, 3, this set 1, 1, 1, hydrogen at number 1, your proton number 1, same element, but the mass numbers are different. Hence, these are isotopes. And where are these placed in your periodic table? That is being not explained by him. He could not explain anything about the positioning of the isotopes. So all these are your limitations for his theory. So his theory holds good, no doubt. His theory holds good only till calcium, only till the lighter elements. The heavier elements were not accepting these kind of classification there. Okay, so please note down the limitations also in order there. All right. Then coming up with an interesting thing, Mendeleev's periodic law. Mr. Mendeleev's, he has given us his theory of periodic table. Most of the periodic table what he has given is what we follow also today, right? And physical properties, physical and chemical which properties, physical and chemical properties of elements are the periodic function of increasing atomic mass, increasing atomic, I'm just showing you in an arrow, okay, of increasing atomic mass. What do I mean by increasing atomic mass? Which means he stated that all the elements in the periodic table are placed in such a way that one after the other, every element is showing an increase in their atomic mass. That is what he has said. And he is the one who has first named the horizontal rows. There are a few horizontal rows called as periods. Okay, and vertical columns known as groups. Okay, periods or horizontal and vertical columns are being given as groups. And the best part, what he has done is spaces were left. Spaces were left in his periodic table. He has set one periodic table and places were left in the periodic table for the elements to be discovered, because he has gauged that there must be some element falling into this category, and till date we did not find that element, but there must be some element which when comes up, my periodic table should not get disturbed, right? So therefore he has left some spaces in appropriate positions, leaving the space saying Ica aluminium. He said Ica aluminium is one position he has left. Ica stands for same nomenclature, same like aluminium. It holds the same like aluminium. And then Ica silicon, and then Ica boron. Ica silicon, Ica boron. These are the spaces which he has left out. But that was been a very good move by him, because later on, Ica aluminium is being filled by gallium. Gallium, a metal called as gallium, is being introduced into the periodic table, which has exactly the same properties what he meant for and left the space for. And then Ica silicon is germanium. And Ica boron is scandium. These are the elements which were later being discovered and been incorporated into those gaps, into those spaces left for these elements, so that the periodic table would not get disturbed. So these are the best moves given by him. Number one, he has named them as the horizontal rows called as periods. Number two, the columns were being given as groups, and number three, spaces were left, and it has been given as gallium, germanium, and scandium, Ica aluminium, Ica silicon, and Ica boron. Then what are the limitations? Limitations means what are his problem areas? What are the problem prone areas wherein this system is not being accepted widely later on? Number one, position of hydrogen. Hydrogen position was not being cleared by him as well. Like, because as we have just now discussed, hydrogen behaves as also halogens, FClBri, and also behaves as the group 1 element of Lina, K, Rabdi, sabse fresh, right? Lithium, sodium, potassium, all those elements also it is behaving. But so therefore the hydrogen position is not being given. That is one demerit of it. And number two, increasing atomic mass is being told, but it is not increasing also, because, for example, if I say you have potassium and calcium, you have argon, potassium, and calcium. Argon has got a mass of 40, potassium has got 39, again calcium 40. Now, as I say, increasing atomic mass, argon coming at number 18, this is number 19, and this is 20. 18 to 19, increasing atomic number, fine. But is that increasing atomic mass? Mass is being lowered there. After 40, it is 90. If it is 39, it is wrong. right? So therefore, the mass is not being obeyed by them. So therefore, the positioning number one is different and the mass also is not being accepted. Like for example, other example we can quote cobalt and nickel also. Cobalt is 58.9, although very minor difference, it is 58.7. Cobalt के बाद nickel आया है table में, but as per the rule, what he said, increasing atomic mass, 58.9 should be the later one, but it is not being given there. So hence, his theory of increasing atomic masses is being disturbed there. And the reason for the periodicity is also being not explained. Reason for periodicity is not explained. He said all the elements in his periodic table will repeat its periodic properties in the same column. Every element in the same given column will have the similar properties, what he said. Okay, and why is that having similar properties? The reason for the periodicity is not being explained by him. That is again a flaw. So although his theory is good, his postulates are good, his mapping is good, he has also left spaces which were not being disturbed and the other elements were able to take up those positions. He has named it as rows and columns. The only thing where it is going on wrong is he said these properties of elements have the periodic function, which means the properties of these elements are getting repeated. It has got the similar properties in the next elements as you come down in the groups. But that is not being explained by him. By that, increasing atomic mass concept is wrong because we have seen a difference there. Mass is not increasing here, mass is getting decreased here. So there one flaw we can find. So this theory also is not being completely accepted. Then comes with Moseley's periodic table, which is what we follow today. So the modern periodic table or the Moseley's periodic table. Now coming up with the modern periodic table, Moseley's periodic table. Moseley, he has given us this theory, this periodic table in 1913. This has been widely accepted by everybody, very new periodic table, in fact, right, in 1913. And according to him, the physical and chemical properties of the elements are the functions of their atomic numbers. He has just mended a word in the previous periodic table. Mendeleev's periodic table is nothing but, if you remember that, physical and chemical properties are the periodic function of increasing atomic masses is being given by Mendeleev, and now it is increasing atomic numbers. The atomic masses is been creating a problem. Atomic numbers as it is being increased, there is no problem here. So therefore, he has given us the law that physical and chemical properties of the elements are the periodic function of their increasing atomic numbers, which means what do we mean by periodic function? He says every element in every coming up next element in that particular set, in that particular column, will have the repetition in the properties. And this is what the periodic table given by him. As you can see this, whatever element you talk about, he has given the mass numbers, atomic numbers, their configurations, SPDF configurations, which we have also discussed, right? So now we are not discussing in detail about it. We are discussing about the periodic classification of this particular table, this particular periodic table we are talking about. And he has given us a theory saying that every element in that group, because already the names were being given, horizontal rows are called periods. How many periods do we have? We have 7 periods. As you can notice, 7 periods. Now don't consider this and that. The lanthanum and the actinium here, these the bottom row, you have 2 rows bottom at the bottom. Do not consider these 2 rows. Why? Because these are nothing but the rows here only. I will show you that in a magnified version, don't worry. Now, coming up with this, he has given totally 18 columns called as 18 groups. He has named it as groups, totally 18 groups, 7 rows, which are called as periods. Periods are rows and your groups are your columns. And in between them also, he has also named them differently. First group and second group, as you can notice here, first group and second group, which we प्यार से हम बुलाते हैं उसको, to remember these things are लीना के रबड़ी सबसे fresh, right? And then the second group, we remember beta mange car, scooter, baap, razi, right? Lithium, sodium, potassium, rubidium, cesium, francium, and beryllium, magnesium, calcium, strontium, barium, radium. Group 1 and group 2, both are considered to be, first group is, group 1 is alkali metals. Group 1 is alkali metals. And group 2 is alkaline earth metals. Alkaline earth metals, because their hydroxides are alkaline in nature, which are found in the earth's crust. That's the reason. And group 3 to 12, as you can notice here to here, all from 3 to 12 are called as transition elements. Transition elements. And group 1 and group 2 are purely metals. All these are metals except the hydrogen part. Except hydrogen, group 1 and group 2. But we don't consider group 1, hydrogen, as the group 1 also, because I'll tell you the reason also later. Now, so group 1 and group 2 are metals, and 3 to 12, they are called as transition metals and transition elements, I would say, most preferred transition elements. And then you have 3 to 18, may you have segregation also. 18 is noble gases, and 17 are halogens. Halogens, oxygen family, nitrogen family, carbon family, then boron family, you can go with naming them. Right, and so these elements are they have been classified into groups. Don't go it parallelly, go it group wise, column wise you go. Okay, so according to that, he has given us this as you have 7 periods. 7 periods. First period is the shortest period. First row having only hydrogen and helium. Second period and third periods. The second and third are short, having 8 elements each. First having only 2 elements. Second and the third having 8 elements. Then fourth and fifth having 18 elements. Sixth and seventh having 32 elements. This, I think you can relate this number 2, 8, 18, 32 to 2n square formula. If n is equal to 1, it is 2. N equals to 2, it is 8. N equals to 3, it is 18. N equals to 4, it is 32. So that is how you go with numbers there. Now, these are the numbers given. Now, how is that, ma'am? Numbers are being shown. That is just looking like a rectangular box. But why is fourth and fifth having 18 elements and sixth and seventh having 32 elements? This is what the reason. Let us see here. What is the number that you can notice here? Yeah, here for this. After 56, you're moving on to 71. After 88, you're moving on to 103. So where are these elements? These elements are here in the bottom row, as you can see here. Bottom, we have a couple of rows given. It is a part of 6th and 7th only. See, after 56, it has to be 57. Now, see, everyone is increased 71, 72, 73, 74, 75. Like this, 55 के बाद 56 सही है. 56 के बाद 57 होना चाहिए. It is not there. So 57, here it is. 57 to 70. As you can see, all these are 57 to 70. They all are put under one particular box only, which is called as lanthanium. Lanthanide series. These are called as lanthanides. And actinides. At the bottom also the same thing happened. Dekho, after 88, it has to be 89, but it is 103 after 88. Do you notice that? See, after that 85, 86, 87, 88, 89 where? Where is it? Bottom. So 88 ke baad, you see the have it as 103, the group 3 elements. It has to be given in this box only. And these boxes are nothing but put differently here because there is no space to put those boxes. And why should they be put in the same box? Because they have the similar properties, right? This is called as lanthanide contraction and actinide contraction. Everything to be contracted and put under group. under one box, which is not possible for us. That's the reason we have shown it differently. It is no two different periods. It is the same period of 6th and 7th periods. You have lanthanides and actinoids. Actinoids and lanthanoids are those elements called as. So that is how your periodic table is being classified. And these are the long periods. The longest periods are 6 and 7. Shortest is first period, hydrogen and helium. Long are the second and short are second and third. And the long periods are 4 and 5, having 18 elements each. And longest periods are 6 and 7, having 32 elements each. Now, what are the merits of this? Merits of this, yes, based on the atomic number he has given, where there is no deviation at all, because atomic masses, there are deviations. We have seen that deviations also in the last table. But now in the atomic numbers, there is no such deviation. And he explained the periodicity also, explained the reason for periodicity. Nobody could explain the reason for the periodicity, but he could explain the reason for the periodicity. What is the reason behind it? Let us validate that. So if I say Lina K Rabdi Sabse fresh, jokes apart, yeah, lithium, sodium, potassium, rubidium, cesium, and francium. Having these numbers as I would say 2, how much is that going to be? 2, 1. I'm writing the configurations. This is 281. This is 2881. As you go down like this, if you notice, everywhere you see one only. You see one here only. So everywhere it is just one valence electron in that particular shell. Last shell has got one electron, and hence having the number of valence electron will decide the bonding pattern also, because electrons are the ones which are responsible for making a bond. Whether you make a bond or break a bond or whatever you do, it is the electrons which are responsible for. Now, everywhere you have one electron in the outermost shell, so which means all these elements will have the similar kind of bonding. It is all ready to lose one electron. Similarly, beta mange car scooter mein bhi dekho, beta mange car, as you go down, beta is beryllium, which is 2, 2. This is 282. This is 2810. 10 can be written as 8, 2. So everywhere you see 2 electrons in the outermost shell. So all these elements will behave the similar way of bonding they show because of their valence electrons. So hence the reason for the periodicity could be explained by him. And there is a clear-cut separation of the elements, their names, like their properties, according to their noble gases. He could explain what the noble gases are, why they don't react, because they have 8 electrons in their valence shell. All the noble gases, all the last group elements are all called as noble gases, which have got 8 elements in their outermost shell, which they do not want to react because they are full in the shells. They are at their utmost capacity and they do not want to change themselves there. So therefore, everything is intact there and do not want to react. Halogens and halogens are one element, one electron less from attaining a noble gas configuration. So they all will try to attain one electron by hook or crook. Taking up one more electron, they become negative. All of these elements will behave the same way. These are called as halogens. And similarly, group 1, group 2, everything is been specially categorized to remember it separately, easily, right? And isotopes were also being given position here. Now, there was a clash with isotopes in the Mendeleev's periodic table, saying that, okay, isotopes, where do we put the isotopes? We don't know how to put the isotopes. We don't know the position of isotopes. But mostly, very cleverly, he said, why should his children go here and there? His children should be in his home only, which means isotopes are nothing but the part of that element only, which will be in that particular box only. Like our children will not go anywhere else. Our children will be with us. So hence isotopes are nothing but the same element, same family will stay in one home, right? So therefore, he has given us the beautiful concept of isotopes having to share the same elements space. If I say hydrogen 1, 1, hydrogen 1, 2, hydrogen 1, 3, everything stays back in the same box. That is what it is being taught. So your isotopes were being positioned properly, and hydrogen was not being determined any particular position because hydrogen behaves as group 1 elements. Group 1 is your Lena, K, Rabdi, sabse fresh. It behaves as those elements as it removes one electron, and it also behaves as group 17. Group 17, देखो FClBri, as you can see FClBri, it behaves as these elements also, right? So which means hydrogen is not being given a special position. So because of these things, his theories were being easily identified, easily well known, and everything is being segregated so well that we are using his periodic table as today's modern periodic table. Now coming up with, now this, there is no demerits for it. That's the reason we are using this, right? Now coming up with the properties. Now the important trends in the periodic table, trends or properties of the periodic table. Now, if I have to talk about these properties, and he said that every element in the group will behave similarly, right? Let us see how is it going also. Number one property I have to talk about is atomic radius. Atomic radius or atomic size. As the size, like as the radius increases, size also increases, right? So that is one thing we talk about. Let us talk about that. Now, if I have to talk about in the group what is happening and in the period what is happening, we have to talk about two distinct things always. What happens in a group and what happens in a period. Both the things we have to discuss about. In a group, if I have to talk about, chalo, same example, Li, Na, Ke, Rabdi, Sabse, Fresh, right? So this is 2, 1, this is 2, 8, 1, this is 2, 8, 8, 1. Do you notice an increase in the shells getting added onto it? Every time you come down, each and every shell is being newly added on. So therefore, see what is the exact structure of an atom? Atom has got a nucleus which has got protons and neutrons, and electrons would be revolving around the nucleus, right? Electrons would be revolving around the nucleus in shells, particular shells, in energy shells, wherein these shells will determine the size also. More number of shells you have, much is the size of an atom, much is the radius of an atom. So hence, as you can notice, Li, Na, K, as you come down in the periodic table in the groups, atomic size increases. Atomic size increases. Yes or no? It is increasing because as we have seen a predominant increase in the size there. Now, what happens in a period there? In a period, as we notice, what is periods? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. These are the elements in a period what I have. If we have to talk about that, I talk about lithium as 2, 1, this is 2, 2, this is 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, and 2, 8. These are the ones which we are talking about. Now, if we check out, is there any predominant increase or decrease shown in the shells? I would say no, because nothing is being increased there. But do I say that there is no change in the size then? No, there exists some change in the size, not as predominantly as groups, but yes, periods do show the change. Now, what is the change being shown? Let me talk about the nuclear charge. What do I mean by nuclear charge? Is nothing but the charge on the nucleus. Whatever is the charge on the nucleus is said to be the nuclear charge. Now, what is the charge on the nucleus? It is neutrons have got zero charge, protons have got the positive charge. How many ever protons you have, that much positive charge you will have also. So here 2, 1, 2, 2, 2, 3. So lithium has got 3 protons. So nuclear charge is +3. His +4, +5, +6, +7, +8, +9, and +10. Now imagine the electrons are moving around in the same shell. This is a nucleus. Okay, electrons are moving around in the same shell, but with increasing atomic masses, which means I would say, chalo, increasing atomic nuclear charges, I would say. As the charge is increasing, nucleus is at the center point, right? And as the charge is increasing, the positive charge is increasing, the positive charge will attract the negative electrons, right? Electrons are negatively charged and they will be attracted towards the positive nucleus. So there thereby, as you see one after the other elements, your nuclear charge is increasing. As the nuclear charge is increasing, attraction increases. Now, as the attraction increases, all these elements, all these electrons which are in that aura will tend to come closer, to the nucleus, thereby reducing the size of it efficiently. Initially, it was that white aura. Now it is this blue aura, what it has. Now the size has decreased. So left side elements are larger in size and right side elements are smaller in size. As you notice this, yes, so nuclear charge increases, attraction increases. You can say in a period, what is happening? Nuclear charge is increasing, attraction increases, therefore size decreases, right? So this is one property we can talk about here. With the second property, valence electrons and valencies. So what is happening in a period and what is happening in a group? Group matlab it is downward, period is left to right. Now lithium, sodium, potassium, just few examples I'm showing here. So 1, 1, 1, as you see, valence electrons are the same, right? Valence electron are same in the group. And what is valency here? Valency is +1 only. Everywhere it wants to remove one electron. Similarly, beta mange car scooter, that also we do. Beta mange car. Okay, Be +2 because this is 2, 8, 2, 2. This is 2, 2. This is 2, 8, 2. This is 2, 8, 10. 10 is written as 8, 2. Everywhere you have 2 electrons in the outermost shell. So valence electrons are the same. And valency is +2 here. And similarly, you have halogens. Halogens is what? F, Cl, Br, I, right? So this is what? 2, 7. This is 2, 8, 7. This is 2, 8, 8, 7. So everywhere you have 7 electrons and the valency is -1 here because everywhere you want to grab one electron to become negative. So valency is -1. So what is happening in the period then? Period is lithium is 2, 1. This is 2, 2. This is 2, 3, 2, 4. 2, 5, 2, 6, 2, 7, 2, 8. As you see, valence electrons increases as you move from left to right in a period. And what is happening to the valency there? Valency here, as you can write down, this is +1, +2, +3, plus or -4, and then -3, -2, -1, and 0, because it has to take up 1 electron here, fluorine, -1, takes up 2 electron oxygen, so hence it is -2. Everywhere it is increasing and decreasing. First, so valency first increases and then decreases in the period. So this is the thing which we talk about, valence electrons and valency. This is your property number 2. Next coming up property, very important property, metallic character. And what is metallic character? What do you mean by metallic character? Metallic character defines the electropositivity. Metallic character defines electropositivity. Whichever metal you talk about, they're all electropositive, right? So this is electropositivity we are talking about. So any metal, if it is a good metal, it should be able to donate electron easily and become metal, right? That is what is the metallic character I talk about. In a group, if I talk about, if I say Li, Na, K, rubbery, सबसे fresh, right? This is 2, 1. This is 2, 8, 1. This is 2, 8, 8, 1. As you see here, there is increase in the size observed, right? This is increasing. This is even more bigger size, right? So this is my nucleus there, and even more increasing sizes you find. This is nucleus and this is the aura. I'm not drawing everything there. Okay, so this is the nucleus and the increasing aura. As you can see, the size is increasing. If the size is increasing, will it be easy to remove an electron from the outermost shell? Because everywhere, as I can see, everything is +1. +1, which means every element will remove one electron. Everything will do that. And who will do it much better? Whose ever size is bigger. Because if the size is small, The center part is the nucleus. The nucleus is positively charged, and the electrons revolving there will be attracted if you have if you have less of the distance, right? Less distance, more attraction. More distance, less attraction. Less attraction. As for this, for the last one, as you can see here, and the last final electron is somewhere here. This electron can be easily removed out, and hence, who has the better tendency to become positive? Is that lithium or francium? Huh? So francium has got a better tendency to release an electron because it is much far away from the nucleus. Far away from the nucleus, attraction very less. So therefore, electrons are easily removed for francium. So as we come down the group, what is happening? Metallic character increases down the group. So metallic character is increasing down the group, which means electropositivity is increasing down the group. Now, what is happening in a period? Let us talk about period also. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now we talk about this here. As we could see earlier in the case of size, nuclear charge is what we have to talk about. Nuclear charge is +3, +4, +5, so on, +10. As the nuclear charge is increasing, attraction is increasing. Now, as the attraction is increasing, electrons are much coming closer. As they are coming closer, size is shrinking down. As I can say that here, the left side ones are bigger in size, the right side ones are smaller in size. So who can remove the electron easily? The bigger ones, because the attraction is less. Therefore, the initial ones, these elements could remove the electrons easily. Lithium, beryllium, these can remove the electrons easily, hence better metal. So in a period from left to right, as you move from left to right, your metallic character decreases, which means electropositive character decreases. As the size is small, it is very hard to remove the electrons. Now here we have to talk about one more property, fourth property I would say, or 3A I would say, ionization potential, which is not there in your textbooks, but yes, there is. This point is very important. There is something called as ionization potential. Ionization potential. Okay, or ionization enthalpy. IE, ionization enthalpy, states that the energy required for an atom to remove an electron. See, remember one thing, this is an atom. If you give energy to the atom, the electron comes out. Electron is released out. Remember one thing that, okay, energy is supplied to an atom. Atom gains that energy, and that energy is transferred to the electrons in the outermost space. And these electrons are more prone to go out. So therefore, energy given to an atom, electron is released out. Remember that. So ionization energy is that energy given to an atom to ensure that the electron is going out. So which is nothing but the metallic character we are talking about. So now tell me, as you come down, francium can do that very easily, right? Calcium can release the electrons so easily because of its bigger size. Please try to make it up very important, bacha. The reasoning part is very important here. As you come down in the group, size is increasing. Now, as the size is increasing, attraction is less. So hence electrons are removed out easily. So do we have to give in so much energy to do the job? So we don't need to give them any energy to do the job, right? So therefore, low ionization potentials, low ionization energies as you come down. So in a group, ionization enthalpies come down, decreases in the group. And what happens in a period there? So try doing in the period. So now in a period, what is happening as you move from left to right, left side ones, as you can see here, these left side ones are bigger ones, easily electrons are removed. So if easily electrons are removed, I would say low ionization potentials or low ionization enthalpies for the left ones, and right side ones, it is very hard to remove an electron. As it is hard to remove an electron, why is it hard? Go back to your size again. Smaller size, nuclear charge increases, attraction increases, smaller size. So smaller size, it will be hard to remove an electron. As it is hard to remove an electron, energy should be given in here, more of energy to be given here. So in the period, ionization potential or ionization energy increases in a period. Here it is high ionization enthalpies. I hope you get this point. Whenever we talk about metallic character is the electropositive character, because all the metals, aluminium plus 3, Fe plus 3, Fe plus 2, iron, copper plus 2, copper plus 1. So whatever metal you talk about, every metal is positive. Positive, which means the property defines by removing an electron. To remove an electron, size has to be bigger. So bigger size, easy to remove the electron. So whichever is a bigger size is a better metal. You don't need to give in much energy to remove electron. Their bigger size, if it is a better metal, then low ionization potentials. We don't need to give much of energy to remove that. Is that clear? This figure also to be cleared, bache. If you do not get this, pause it, play back, and then come to me again if you still have any doubts. All right. Next, the last character for the day, number 5. Metallic character done. Then we talk about number 5, non-metallic character. Non-metallic character, which means your electronegativity, or we talk about electronegative character is non-metallic character. Now, as in the group, let us talk about the group first. Li, na, ke, rubdi, sabse, fresh, right? This is smaller, bigger, much bigger, right? So as the size is increasing, non-metallic character talks about electronegativity, which means taking up an electron. Who can take up an electron? Is that the lithium or francium? Who is responsible to take up an electron? Electron is the negative charge. It has to be attracted by the positive of the nucleus, right? So the size, if it is small, which means the distance is small, attraction is more. So hence I would say the top ones are better non-metals. So therefore, electronegative character decreases down the group. As you come down, it is very big. No? If it is very big, can you take up an electron? We can't take up an electron so easily, right? So therefore, better non-metals are the top ones. So non-metallic character decreases down the group. Okay, this is one point to be clarified there. And what happens in a period? Period also lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Left side ones are the bigger ones and right side are the smaller ones. Go back to the same reason there. Nuclear charge increases, attraction increases, therefore size shrinks down for the right side. Now what is happening here? Here if you see non-metallic character, which will be right side, you have more of non-metals. These are better non-metals, I would say, because smaller size will be able to attract the electron easily, and we have to attract electron easily if it is a non-metal, right? So better non-metal. So non-metallic character increases in a period. So you have a better non-metallic character. So non-metallic character increases in a period. Now here we have to talk about a property called as electron gain enthalpy. Electron gain enthalpy. Now, what do you mean by electron gain enthalpy? It is nothing but the energy that it has to lose to gain an electron. See, remember one thing, if an atom is gaining, this is your atom, you again figure it out this part. If an electron is coming in, it has to release energy. Atom should release energy if it has to welcome an electron. See, imagine this imparted to your normal human nature. If you have to welcome some guest, you have to spend a lot of money, you have to spend energy, right? You have to spend time, you have to release energy to welcome some guest, and the guest you are welcoming is an electron there for an atom. right? So atom has to come in, energy has to be released. Remember that point. So electron gain enthalpy, the energy released by an atom in order to gain an electron. Now, whoever has got the better tendency to gain up an electron will release a lot of energy. Whoever has a better tendency to gain electron will release a lot of energy. Now, out of these two, top and bottom, lithium and francium, lithium has got a better tendency to gain electron because of its size. Hence, it releases a lot of energy. So, high electron gain enthalpy here on the top and low electron gain enthalpy on the bottom, because francium does not have the tendency to gain electron. So therefore, it does not have energy to lose also. It does not have a tendency to lose the energy also. Now, same thing come to the period there. So here, electron gain enthalpy decreases. It is decreasing in the group. Now, period में क्या हो रहा है? Period में you can see right side ones are better non-metals. They have a better tendency to gain the electron. As they gain the electrons, they have high electron gain enthalpies, and obviously the left ones have got low electron gain enthalpies. So this is about your non-metallic character and electronegative character, which is nothing but, and which will be defining us with the electron gain enthalpies. Enthalpy is nothing but the energy there. Now, I think we missed out one point, one last point to be talked about. Now, size we have talked about. Now, according to the size, as I told, size is increased in the level, is more in the left side. And as you come to the right side, your size is getting decreased, right? So, but there is an exception here. Fluorine to neon, halogens and your noble gases. Size, radius of halogens is less than radius of noble gases. Remember that. Actually, according to the trend, halogens ka size should be more, but halogens of size of halogen is less than noble gases, because of their good amount of space available, electrons are all happily sitting in their orbitals very freely, thereby a small increase in the size as compared to the halogens only is observed. But rest all will go by the trend, but only the halogens and noble gases that will go on a reverse trend. Halogens are having less radius. This is radius, okay, than compared to the noble gases. So this is all about your periodic classification, the models of the periodic classification, models of the periodic tables that we have, and the trends in the periodic table to be followed. So everything in detail about this chapter, and please do it well to answer some of the questions. I'll be posting you some questions based on this also. I want you to answer them and get back to me on the next day whenever you come to the class. And please do ask the doubts then. All right. So that's it for today, and happy learning. This is Harita Kasturi from PACE IIT and Medical Hyderabad signing off. Bye-bye. See you all, bacha. Happy learning to everybody.